Good evening. This is our research paper on Silverline towards data confidentiality in storage intensive cloud applications by Putswami, 2011. Presented by Brandon, Dhruv, James, and myself, Sean. The problem statement goes as following. With the elasticity and availability of the cloud has become more and more popular, however, this technology comes with many risks, including software bugs, operator errors, and external attacks that could compromise the confidentiality of application data on external clouds. Furthermore, current methods of cloud encryption are limited. For example, many organizations will encrypt all data before it ever touches the cloud, which will satisfy security requirements, but also leaves data static, meaning there can be little or no computation performed on the data itself. A solution to this. So first, we're just going to get agnostically without going into Silverline just yet. But this is what's proposed as a solution to the two previous slides. So here you can see Alice and Bob. And first off, you can see the arrows where they're getting their keys from the organization or central point. And then they encrypt the data first and then send it to the cloud. When the users want to pull their data, they can pull it encrypted while getting the decryption keys from their organization again and decrypt it on their local machines. So that's the solution. It seems trivial, but there are some complications that we're going to discuss shortly. Yep. So what is Silverline? Just the high-level definition is it's the implementation of techniques and a protocol of software tools designed to simplify the process of securely transitioning applications into the cloud. Some of the challenges to Silverline. One is identifying functionally encryptable data. So we present, or the author presents, an automated technique that marks data objects using tags and tracks their usage and dependencies through dynamic program analysis. Then we have encryption key assignment. So automatically infer the right granularity for data encryption that provides the best trade-off between robustness and management complexity. And third is secure and transparent user data access. So edge or client devices need to be given decryption keys by the organization to provide users with transparent data access. Of course, these devices must protect these keys from compromise. A proposed method is client-side component to prevent key compromise. So if you look at this slide, this is a demo schema put together by the author. So imagine this is a database for, say, an online chat service. So this is something that would have value when we discuss in Silverline because of the straightforward data being stored. So imagine you just had a select query looking for all the records matching user ID Bob. It does not need to interpret the actual string, and it would succeed if the string was encrypted. Now the system will determine the type of encryption and granularity. Sure, we can use one key and encrypt all of the data, or we can encrypt each object, but those are both extremes. It would not be smart in terms of security and performance, respectively. The solution is to cut the data into subsets. So imagine if Bob and Alice were in the same group chat, you can encrypt that as a subset instead of encrypting both Bob and Alice itself. And now I'll give it off to JJ.
Thank you, Sean. Silverline's data partitioning scheme is designed to ensure data confidentiality in storage-intensive cloud applications. The scheme splits the data into multiple fragments and protects each fragment with a unique encryption key. The fragments are then distributed across multiple servers to ensure that a single server does not have access to all the fragments of a given data set. The first step in the data partitioning scheme is to fragment the data into multiple pieces. It is broken up into fixed-size blocks, and each block is encrypted using a symmetric encryption algorithm. The system then generates a unique encryption key for each block, which is used to protect the block. After the data is fragmented and encrypted, the system distributes the data across multiple storage servers. The distribution is done in such a way that ensures that no single server has access to all fragments of a given data set. The distribution scheme is also designed to ensure that the system can handle changes in the workload without compromising data confidentiality. Silverline's data partitioning scheme is designed to handle dynamic workloads by dynamically adjusting the data partitioning and distribution scheme. The system uses a workload manager to monitor the workload and adjust the data distribution scheme accordingly. This ensures that the system can handle changes in the workload without compromising data confidentiality. Silverline provides efficient updates by adding a secure update mechanism that updates only the necessary data fragments. The system uses a version manager to keep track of different versions of the data fragments, and when an update is required, the system updates only the necessary fragments and creates a new version of the data set. Now we'll hand over to Drew to discuss the details of key management.
Thank you, JJ. So the encryption key used in key management are used to protect the data fragments and are stored on separate key servers, which are not accessible to the storage servers. The key servers are responsible for managing the encryption keys and providing them to the storage servers as needed. The use of separate key servers ensures that the encryption keys remain confidential, even if a storage server is compromised. Silverline allows users to decrypt and access encrypted data on their device by providing them with the necessary keys. Users can access data without requiring a network connection, which ensures that Silverline is available even when the network is not. Silverline provides two mechanisms for key delivery, which are push and pull. In the push mechanism, keys are sent directly to the user's device, while in the pull mechanism, users request the keys from the organization as needed. Silverline also provides a key caching mechanism on user's device, which allows users to decrypt data even when they are offline. Silverline ensures that the access control policies are enforced on user device at all times, thereby preserving the confidentiality of the data even when it's outside the organization's control. Then we talk about the application modifications and the responsibilities when using Silverline. So Silverline requires minimal modifications to existing applications to support encryption and decryption of data. The organization is responsible for modifying the application to use Silverline for encryption and decryption. Silverline provides a simple API for encryption and decryption of data, making it easy for developers to integrate it into their applications. The organizations are also responsible for defining access control policies for data and managing the keys. At the same time, Silverline ensures that the access control policies are enforced by encrypting data at rest as well as in transit. And finally, the organization is also held responsible for managing user accounts and ensuring that the users have access to the appropriate keys. Silverline provides a secure and efficient mechanism for storing and managing keys as well, which reduces the organization's hardware cost and infrastructure requirements. Talking about confidentiality versus key management, confidentiality and key management are both important considerations in protecting the data in the cloud. Confidentiality ensures that data is only visible to authorized parties, while key management ensures that only authorized parties have access to the keys that allow them to view a particular set of data. In Silverline, confidentiality is achieved through fine-grained encryption, where different parts of a single table or even individual cells may be encrypted with different keys. Key management is the responsibility of the organization, as we saw in the previous slide, which must store all the keys securely and provide users with only the keys they should have access to. By taking a fine-grained encryption approach, Silverline provides strong confidentiality guarantees while minimizing the risk of key compromise. However, effective key management is critical to maintaining confidentiality, and organizations must ensure that the keys have adequate measures in place to securely store and distribute keys. Talking about integrity of the data on the cloud, in addition to confidentiality, the integrity of the data on the cloud is also a critical concern for storage-intensive cloud applications. Silverline provides integrity guarantees by leveraging the fact that all data is encrypted before even being sent to the cloud. By using authenticated encryption, Silverline ensures that data cannot be tampered with without the tampering being detected. Silverline also allows for the detection of replay attacks. Replay attacks are when an attacker intercepts and retransmits data to the cloud to modify it or cause an application to malfunction. By detecting replay attacks, Silverline ensures that the data on the cloud remains consistent and accurate, providing a robust integrity guarantee to storage-intensive cloud applications. Next, we talk about encrypted data tracking. Silverline relies on encrypted data tracking to maintain data confidentiality and integrity. Each encrypted data item is associated with a unique identifier and its corresponding encryption key. When a user attempts to access an encrypted data item, Silverline verifies the user's identity and authorization level. The system then retrieves the encryption key for that specific item from the organization's key management system and decrypts the data for the user. The decrypted data is never stored on the user's device and is erased from the memory once the user is finished with it. When a user updates an encrypted data item, Silverline re-encrypts the data with the appropriate key and updates the tracking system accordingly. In figure 3, the figure shows how data is encrypted and decrypted using various keys and how the system keeps track of the data and its corresponding keys. The process starts with the application server receiving a request from the user. The server then checks the access control policy to determine if the user has required permissions to access the requested data. If the user is authorized, the server retrieves the encrypted data from the database and sends it to the user. The user then decrypts the data using the appropriate key. The key used for decryption is determined by querying the key management service. The key management service maps the user's identity to the corresponding key and returns it to the user. The user can decrypt the data using the key and view the plain text. When the user updates the data, the application server encrypts the updated data using a new key and stores it in the database. The old key is marked as invalid and the new key is stored in the key management service along with the user's identity. The key management service then keeps the track of all the keys and corresponding encrypted data, ensuring that the correct key is used to encrypt the data. In case, even if a key is compromised, the key can be revoked by marking it as invalid in the management service. The compromised key will no longer be used for encryption or decryption, and the data encrypted using that key will remain inaccessible. Finally, we talk about the database labeling and key assignment implementation in the system design of the Silverline. The figure shows the process of determining the encrypted data for each user based on the user's privileges, assigning keys to the encrypted data and creating a mapping between users and the keys they have access to. The process begins with the organization defining the data schema for the database and labeling each column with a set of access control policies. The access control policies determine which users have access to each column of the database. Silverline generates a set of symmetric keys, one for each unique access policy. Each symmetric key is then used to encrypt the data that corresponds to the columns with the corresponding access policy. For instance, a user's email address and location information might be encrypted with one key, while the name and phone number are encrypted with the another key. Once the data has been encrypted, Silverline generates a mapping between each user and the symmetric key and symmetric keys they have access to. This mapping is stored in the key assignment table. When a user logs into the system, Silverline retrieves the key assignment table and uses it to determine which key the user has access to. The user can then use those keys to decrypt the encrypted data, and that corresponds to their privilege. Now I will hand over to Brandon, who will discuss about the database dynamics as well as the incompleteness and how Silverline aims to address those issues.
Thank you, Dhruv. Yeah, here I'm going to talk about Silverline incompleteness and database dynamics. Incompleteness is when there is a chance of incomplete data in the cloud. Database due to network outages, server failures, or human errors. Database dynamics or cloud databases when dynamic, with records and attributes added and deleted over time. These changes affect the encryption key management as new keys must be generated and existing keys must be revoked or updated. Silverline's design handles these issues with the help of a centralized key management system that tracks data and key assignments, detecting changes and generating new keys accordingly. The figure above shows that the user interacts with the cloud applications through their device, and the device sends a request to the Silverline system. The Silverline system receives the request and authenticates the user to ensure that they have the necessary permissions to access the requested data. Next, the Silverline system consults the metadata database to determine the appropriate keys to decrypt the requested data. If the requested data is labeled with a symmetric key, the system retrieves that key and uses it to decrypt the data. Otherwise, if the data is labeled with a public key, the Silverline system retrieves that key and uses it to decrypt the symmetric key that was used to encrypt the data. Once the requested data has been decrypted, the Silverline system encrypts it with the appropriate keys and sends it back to the user device for display. The figure also shows that the metadata database is periodically backed up to ensure that the organization's data remains secure in case of a system failure or attack. I'm also going to go over the implementation of Silverline as well as the limitations. Starting with implementation, encrypted data tracking code was used to utilize the tag propagation policies by basing the code for PHP taint, the modification to the PHP interpreter, and the PHP MySQL interface were both used on this conduct. The implementation logs a warning every time a tag data item is used in a computation. After interpreting such logs, the logs are then analyzed in order to see which cells can and cannot be encrypted. All evaluation applications use MySQL as the backend database. Labeling in a MySQL proxy was implemented in between the database and the PHP runtime. For each of these applications, the following setup was utilized in order. 1, a database was created with the exact same schema used in the application. Then a sample data was inserted into the database to create a training database for labeling. Then all select queries were identified in the application that read data from the database. Database labeling was then performed on select queries on the applications. And then finally, you analyze the labels attached to the cells to verify the data classification and key assignments performed by our techniques. Sorry. At this time, going into the limitations of Silverline. At this time, not all data in the cloud database can be encrypted. Developers understand this limitation and they are currently working on future work to better the security feature. Cloud cannot currently run queries if encrypted data is randomized. So basically only one set of ciphertext can be read by the database currently. If another type of encryption is called for, it won't be able to be queried at all in the database. Currently, comparison queries on encrypted cells do not work. For example, select star from messages where message ID is greater than 10. Also, this is also expected to be resolved in future work. And all regulated registered users share one single key, which is a tax on community data. Any data that is encrypted with one single shared key is vulnerable to a variety of attacks by the cloud. This leaves room for potential known plain text or distribution-based attacks.
So there has been a lot of work done on Silverline so far, but there's still some work that remains. So classification labeling. There needs to be an intuitive reasoning for such classification, which would be more helpful for the developers and later implementing encryption and decryption functionality in the applications, and automatic partitioning. So Silverline is planning on extending to automatically partition applications and move sensitive data and its computation to client devices. So to sum things up, what Silverline does is promote data confidentiality on the cloud using end-to-end data encryption. It determines an optimal assignment of encryption keys that minimize key management overhead and the impact of key compromise. And it demonstrates the viability of our approach by applying our techniques to several production applications with a mix of commonly used features. JJ.
This paper, as you can expect from a seminal work of this nature, doesn't suffer from a lot of weaknesses, but there are a few things that can be clarified or improved. We'll start, however, with the paper's strengths. This is an exceptionally well thought out paper. The authors really have put forward a lot of effort covering every possible scenario where Silverline could be implemented. There is a deep discussion about what to do in every main case and a number of edge cases. The system has already been described in this presentation, so I won't belabor the point. I will point out the paper's main contribution, which is a system that can be applied without much in the way of retrofitting to most applications on the web as they exist right now. The system runs seamlessly in modern HTML5 compatible browsers, and the encryption needed is performed without the need for any special plugin. The end result has a ground security level far above the baseline, and for not much cost, either computationally or in real dollars for retrofitting. There are a few weaknesses that can be pointed out, mainly things that require rethinking due to the age of this paper. Primary among these is there a need for this system at all in a modern cloud computing environment? When the paper came out in 2011, the cost for naively encrypting and decrypting all the data in the cloud on demand was deemed too computationally expensive. Is this still the case? There are, as the paper points out, some strong incentives for making such a system viable, and dividends in the form of confidentiality. Also worth considering is the approach to data encryption. This paper offers, perhaps by design, no comprehensive solution for what forms of cryptography would be best for the application. More glaring omission is the lack of suggestion for key transfer systems, which are simply stated to be the responsibility of the host organization. With the contributions of the paper so tightly coupled with key management, no commentary on how this could be accomplished was somewhat jarring and unexpected. Keeping on the key vein, the last major weakness we observed is the need for rekeying in the event of a role change. The paper discusses this possibility at length, but does not offer a really good solution, only acknowledging that it is a high overhead situation. Given the commonality of role changes as something that might be expected on a reasonably regular basis, it would seem a good solution should be a high priority, or at least the focus of future work. It would seem that it is neither. Silverline, towards data confidentiality and storage-intensive cloud applications, is a seminal work in the area of cloud security, and it deserves this place. With 146 citations on Google Scholar in such publications as ACM, where the paper itself first appeared, and IEEE, continuously from when it appeared in 2011 until the present year, the impact of this work is readily apparent and will continue to be felt in years to come. Thank you.